about differentiation of composite functions by chain rule. So we'll do some more application examples of that, and we'll wind up differentiation with that, and then we'll move on to integration. So let's begin. Okay, so
Sir,
yes. Differentiation by chain rule. So we saw that if you have a composite function f of gx, then what?
So we have done this topic.
Yeah, I told you I'm taking a recap of that.
Okay.
So the first step that we do is we substitute gx as a dummy variable. So y becomes f of z. So then the second step is we use the chain rule. And the final step, so when we use this, this becomes derivative of f applied on gx multiplied by g prime x. Okay. And finally, resubstitution. So actually, this step comes with the resubstitution. So this becomes okay. So this is what our application of chain rule looks like, and this is what we discussed in the last lecture. So let's look at some couple of examples of application of this, then we'll move on to further things. Okay. Just try out these three and send me the answers on the text message. Once we complete these questions, we'll move on to the next section.
So
Yes, what is the question, beta?
So can you please read what you have written in the step 1?
Gx is equal to z. That's the substitution step.
Okay, thank you, sir.
Okay, people. So hope you have at least worked out the steps of the first one. So I'll just take you through it. So the critical step is actually the first step only, deciding the substitution. Now, what we will substitute to make the integration, sorry, make the differentiation simple. So you can see that it is e raised power sin x. Okay. So if you think of it like f of gx, what is the f over here? It is the exponential function. And what is the g over here? It is sin x. So it's e raised power sin x. So your g is sine, and your f is basically the exponential function. So that is what you have to understand over here. So our first step is the substitution. So you introduce the dummy variable. So you substitute sin x as whatever symbol you like, but I've taken z. So that's our dummy variable. So once you've done that, so y becomes e raised power z, which is now a simple function. Okay, so that's your first step done. Now your second step is the chain rule step.
So this whole procedure is known as what?
Application of chain rule, differentiation by chain rule. All the three steps are part of the application of chain rule. Okay. So now
Sir,
to do this differentiation, see, yeah.
how do we decide which function we have to substitute?
So that is the thing. So you have to understand like which is the inside function, which is the outside function. Like gx is what we've operated on x first. Na? Like you can think of it like this, that suppose see what a function does. When you are given some value of x, you can calculate the value of y from that. Na?
Yes, sir.
Okay, so now think of this function. In this, suppose I have taken x as pi by 6. So I want to calculate y. So what is the first thing I have to do? Do I have to calculate e raised by x or do I have to calculate sin x?
Sine.
Sin x.
I have to calculate sin x. So that is your inside function now. Now you understood, no?
Yes, sir. Understood. Thank you.
Yeah, so that's always you ask yourself that question, that how do I get from x to y? So from x to y, I have to first operate g. Na? So in this case, I have to first operate sine. So I'm getting sin x. That's my gx. And then on that, I'm putting the exponential function. So that is my f. Okay, so f of gx. So that's how we realize which one is f and which one is g. Okay. So
Yes, sir. Got it.
yeah, so if ever there's any confusion that which one you should take as z and which one is the outside function, just think that some arbitrary value of x and how you will calculate y from that. So immediately you'll understand, okay, which one is the inside function, which one is the outside function. First calculate this thing, that sine of pi by 6. Now you know that is half. So therefore y is e raised power half for root. So that's how you understand that for this value. So you understand this process. Okay, so now that we have reached this second step, so now you need to see, okay, how to calculate dy by dz. Just substitute y from here. We've just got it as e raised power z, and then multiplied by dz by dx. So z is what it is, sin x.
Sir, why z is not put into dz upon dx?
Yeah, sorry, some connection issue with my internet. Actually, today with the amount of rainfall, problem with the internet all day. Sometime or the other.
Today it's raining horribly.
Yes,
Yes.
even
All
in
of
other,
yeah,
even in
don't-
school, we were facing problems.
okay, okay. But luckily, you don't have to go out right now. No? If you had to go to school or college in this weather, it'd be crazy.
Yes,
Okay. So anyhow, let's get back to this question. So up to this step, you understood. No? Now we have to execute this step. So the second thing, z has to be substituted as sin x. Okay. And then we have to just apply the normal rule of differentiation. So exponentials functions differentiation is itself, we saw last time. So differentiation of e raised power x is e raised power x. We had learned this as a formula. So therefore, differentiation of e raised power z with respect to z will also be the same. It will be e raised power z. Just the name of the variable is changed. Rest is the same thing.
yes,
So that becomes this, and sin x is differentiation we know is cos x. So we're done with the second step. Now the only thing we have to do is we have to remove z because that's the dummy variable we have introduced. So we have to resubstitute. We have to resubstitute here. We have to resubstitute z as what? Sin x, because that's what we had. Okay, so that will give us the final answer that dy by dx is equal to, now I'll just write it in reverse order, cos x into e raised power z, which is sin x. So this becomes my derivative. So this is the differentiation or the derivative for this given function. E raised power sin x is derivative is cos x into e raised power sin x. Okay, so hope all the steps are clear in this. Now what I'd like you to do is go through this very carefully, okay, and try and apply the same steps for the second question. That 1 upon square root of x square plus 2x. The critical thing is again your substitution step, the first one, that what you have to take as the value of z. Once you're through with that step, you'll see rest is just about working out the steps, like working out the algebra part, like doing the differentiation, substituting, all those things.
Sir, thoda sa can you do of second one?
See,
Only
the thing,
step.
if I give you the hint that what is z now, then the question is over there. And so I'll give you this
Okay,
one.
sir.
I think like I told you in this, now that how to decide that. So given some value of x, how will you calculate y? Think like that. Like if I ask you what is the value of y when x is equal to 1 or x is equal to 10, so how you would proceed? So the moment you think along those lines, then you realize what is the inside function and what is the outside function.
Okay, sir.
Okay. Yes, Rishita, good. You have got the answer. Only just the numerator better. Just be careful about the numerator. There's one more term in the numerator.
okay, sir.
Yeah. See what you've taken as your z, na? So when you do dz by dx, I think you just missed one part over there.
Yes, sir, I saw. Sorry, sir.
Got it now, na? Understood?
Yes, sir.
Good, good, good. So finish that one and come to the third one also.
So,
Okay, people, so I'm working out the second question now.
So,
Yeah,
the thing which you did after step 2, just can you just explain it once?
in this one, in the first one,
No, sir, which you wrote in the blue pen.
above this part, after
No,
step 2,
sir,
this.
that pi by 6 one.
I said that is not important, beta. That was just to give you an example to understand how you realize what you have to substitute. So it's like if you are calculating the value of y for x equal to pi by 6, then how you will calculate? First, you will calculate sine pi by 6. No? It's half. Then you will put e raised power half. So what is the first step? The first step is sin x. The second step is e raised power sin x. So that's why you have to substitute sin x as z. Got it now?
Yes, sir.
Okay. So let's come to the second one. So y is equal to 1 upon square root of x square plus 2. Okay. So you can see that this is like, again, it's a two-step process. Y is 1 upon square root of something. So that's something you can think of as gx. Huh? So it's f of gx. Where what is f basically? F is the function 1 upon square root. And what is g? G is the function x square plus 2x. Okay, so from x, you're first operating g to get gx equal to x square plus 2x. Okay. And on that you are operating. So what is your first function? It is this function. It's whole square plus 2 times. So you're getting that one. So it's that quadratic function. So it's a quadratic function, this one. Okay. And then on that you are operating f. So that you are getting as y as f of gx. So what is that f actually? That f is the function 1 upon square root. So operating that on g. So you're getting that as 1 upon square root of gx. And that is nothing but 1 upon square root of x square plus 2x. So just thinking about this once, that how to get some value of y from a given value of x. It makes it clear that it's a composite function where you have to take gx as x square plus 2x. So y is becoming 1 upon square root of gx, which is f of gx. So once you're clear with that, now you know how to apply the steps. So first step, substitution. Z should be taken as x square plus 2x. That is your gx. This is our substitution step. Okay. So y becomes what? It becomes 1 by root z, or you can write it as z to the power minus half. So now your second step, chain rule. Okay. So I will just to show you that how we can actually save a bit of time here. We can now directly do this in differentiation. You can see that this is your function of z. So what will be dy by dz is differentiation of this. So differentiation of z to the power minus half is minus half into z to the power minus 3 by 2 into dz by dx. So for dz by dx, I will substitute z as this. So differentiation of z is what? It's differentiation of x square plus 2x. So differentiation of x square is 2x, differentiation of x is 2. So that's it. So now I simplify this a little bit more. So I can write this as 2 times x plus 2, okay, divided by, with the minus sign, I can take z in the denominator. Okay. So that's minus of x plus 2 upon z to the power 3 by 2. Okay. Now the final step, I have to remove z from my equation. So I have to
How
resubstitute.
2 times x plus 2?
You take
X plus
sorry,
1.
x plus
No?
1. My mistake. Yeah, my mistake. Sorry. It should be x plus 1.
Sir,
This is what
can
you were saying.
you, sir,
Yeah.
can I explain how you got z raised to power minus 3 upon 2?
Okay. X to the power n rule, beta. Differentiation of z to the power n is nz to the power n minus 1. I would just put n as minus 3 by 2. Sorry, minus half.
Sir, step 1, how did you do?
Step 1, I have substituted in this function the quantity inside the square root as z. Na? So what is y now? 1 by root z. Got it? Na?
No, sir, I didn't understand.
I just substituted x square plus 2x as z. So y is 1 by root z.
Acha, okay, acha, okay. Yes, sir, yes. Sir.
Now I've reached up to this step. I've got dy by dx, but only I've got it in terms of z. So I need to resubstitute z because that's a dummy variable. So I'll resubstitute z as what? X square plus 2x. So on resubstitution, I get this as minus of x plus 1 in the numerator, right? Divided by z, which is basically x square plus 2x to the power 3 by 2. Okay. So now the answer is matching, na, Rishida?
Yes, sir.
Okay. So just finish writing this one, and also if you've done with this, then try out the third question. Was I think ln of sine square x, right? You wanted to find dy by dx. So
It is compulsory to find out n.
it's compulsory to find out.
N.
Didn't get you it. Compulsory to find what?
So now you show no d upon dz is equal to nz raised to n minus 1. So it
This
is
is the
compulsory.
formula, beta. This is the
Sir.
formula we are using.
So no, it is compulsory to find n.
अपने तो कैसे differentiate करेगा बता? If you don't know the value of n for the given function, how you will apply this formula?
सर तो लास्ट सम में n नहीं ढूंढना था ना.
अरे लास्ट सम में ऐसा डिफरेंशिएशन था क्या पता? लास्ट सम में किसका डिफरेंशिएशन कर रहे थे? sin x का ना? Is sin x of the type x to the power n?
हाँ
हो ना?
वही.
Is exponential function of that power type हो ना?
तभी न्यूमेरिकल वैल्यू होगी तभी करने का है.
But I think you need to once revise the basics of differentiation then, na? Because see, you have to understand that this is an exponential function. This is a trigonometric function. Okay, all this. This is a function which has, whether it is x to the power half, or it is 1 upon x to the power half, or it is 1 upon x to the power 5, or it is x to the power 100. These are all examples of which type of function? Power function. So for power function differentiation, which rule we use? This one. So wherever, whatever type of function we have to use that formula of differentiation. No? Understood, no?
Got it.
Now I can't use the exponential function formula for x to the power half. No? And like that, I cannot use the formula for x to the power half for sin x as differentiation.
Yes,
Each function has a type, so it has a particular way of differentiation.
Okay, sir. Got it.
Sir, in the third one, there are 3 functions.
Yeah, there are 3 functions, so it might look complicated, but then I'll give you a hint. Is there some property of ln that you can use? Remember, I told you there are 3 properties of ln.
Yes, sir.
So see if we can simplify using that property.
Okay, sir.
See, what were the properties? That ln of a plus ln of b is ln of a into b. That was the first one, right? Then ln of a minus ln of b is ln a by b. That was the second one. And the third one was the power one. Ln of a to the power n is what? It is n times ln a. Okay, so this is one property. There's another property. This is not being used here, but the first one is being used. And this is the third one. So always remember, whenever we have some ln based function, And if possible, you have to simplify it, then you can use any of these three.
Okay, sir.
So luckily we don't have to substitute twice here, no? Because we can simplify it. Yeah, very good, Rishita. Your answer is correct. Okay. So
सर
here the
1 मिनट ऊपर एक बार इसको रोल कर दीजिए.
okay.
Sir, even I sent you the answer.
Okay, I'll check better. Just a second. Yes, very good. And I think your answer is correct. Okay, so let's move on to the last question of this set. So in this question, it would be convenient actually if we first use the property of log, which I told you. Instead of trying to differentiate sine square x, which is again a composite function. So first we use the property that natural log of anything to the power n, you can just bring the power outside as a coefficient. It becomes n times ln. So here it is natural log of sine x to the power 2. Now sine square x means that. So we can say straight away from the property that this is 2 times ln sine x. Now that 2 is just a constant outside, so it will not bother us. Okay. So now we can go ahead with our understanding of composite function, that that on x we have first operated sine. So I've got sine x. So the inside function is sine x. And on that I've operated twice of ln. That twice is just a constant. So I've got twice of ln sine x. So it's a 2-step process. It's not a 3-step process. So this is my g, and this is my f of gx. I know that this has to be substituted as z. So our substitution step becomes clear. So substitute sin x as z. So y becomes 2 times ln z. So next our chain rule. dy by dx is equal to dy by dz into dz by dx. So this is your y, 2 times ln z. So differentiation of ln z, that differentiation of ln is 1 by x. We saw this as a formula last time. So likewise, differentiation of ln z with respect to z. Just the name of the variable is changed to z. Rest the formula is the same. So this first thing is 1 by z, and then z is sin x. So differentiation of sin x is cos x. Okay. But there's also the 2. So there is coefficient of 2. Okay. So now you can see the final step. We need to just resubstitute. So dy by dx becomes 2 times cos x upon sin x, which you may simplify further and write as simply 2 cot x. So this is also correct on its own. This is also correct on its own.
Done.
Okay, understood. Now, now see, if I had not done this application, it would have been a little bit tricky. Actually, I'd also like you to finish up with one more question. We must have done a question like this in the last lecture, but still just for practice, because this type of question is going to be important for us a lot in future chapters. So if I have y is equal to sine square x, then find dy by dx. Okay, and find its value, the value of its derivative at x equal to, let's say, pi by 6. Okay, so given that y as a function of x is sine square x, you also want to find the value of its derivative, that is the value of dy by dx at the point x equal to pi by 6. So this will also, for example, show you that if I had not simplified by taking ln sine square x as 2 times ln sine x, how I would deal with the inside function being sine square x. Manas and Ayan, just check your steps once, both of you. Yes, Rishita, your answer is correct. Now we have to calculate the value also.
Yes, sir, I'm calculating.
Okay, very good. So the answer should be 2 sin x cos x, or sin 2x also you can write that as, and the numerical value will be root 3 by 2. So dy by dx here should come out to be 2 sin x cos x, which you can also use the sin 2x formula in trigonometry. Get this? Okay. And the value of dy by dx at x equal to pi by 6 will be root 3 by 2. Okay. So this is actually equivalent to this in trigonometry. So if you don't know that from trigonometry, it doesn't really matter. This is, you leave your answer as 2 sin x cos x, that's fine. So let's understand how we have got here. Okay, then I will also connect this to the previous question and we'll understand the point over there. So in this, what you've done is on x
So-
we have opted sin. Yes.
Can't we take it as sin x whole square and then x to the power 2? In that way, can't we solve it?
So where is x to the power 2? We have never done x square, na beta? We have done sin x's whole square. That's the whole point, no?
Yeah,
So it's
so
a composite function.
we'll take
It's a
sin
composite.
x as dx
Sin x as
and
gx.
then the whole
Correct.
square as fx.
That's what we have to do. You have to treat your sin x as your gx. So then your whole square of that is like basically sin x's whole square. So that's your sin square x. So this is your f. F of gx is sin x's whole square. So that's what you have to do now. So you have to substitute here sin x as z. Okay. So your y is becoming z square. So that's why in your chain rule step, so that is becoming 2z into cos x. And then your resubstitution step. Your z is sin x, so it becomes 2 sin x into cos x. So this is the process, okay?
Sir,
So,
Yes.
so can't we do this by product rule?
yes,
By,
sir.
by
Same.
writing
very nice.
sin x and sin x.
Very good, very good. You can do that. That's a completely alternate way of doing this question. And in this case, that's very valid. Okay. You can just write it as sin x into sin x into. So it becomes sin x into differentiation of sin x plus differentiation of sin x. The whole thing into sin x. And that's it. You get the same thing. So if you've done by this method also, it's good. It's an alternate way of doing the same thing. Okay. We'll do this also. Okay. Now to connect this back to the earlier question we did, this one, y is equal to ln of sine square x. If we had not used the property, then we could have done this also, that substitute z as sine square x. So y would become ln of z. Okay. But now when you are using the chain rule, you have to refer back to this problem. Okay. Or again use chain rule once more. Because when you're doing dy by dz itself, dz by dx. Now this is also a composite function, so sine square x. So ln z's differentiation is 1 by z, that's okay. But this thing we'd have to borrow it from here. We're seeing here that differentiation of sine square x is what it is, 2 sin x cos x. So all these steps that we have done, we have to understand those steps and then substitute that here because z is sine square x. So this would be into 2 sin x cos x. And then we do our resubstitution. So that would show us that, okay, z is how much? It was sine square x. So it is 2 sin x cos x upon z, which is sine square x. So finally we would come to the answer that is 2 cos x upon sin x. So that's why I told you that this is a more complicated thing. If we don't use the simplification and straight away go into differentiation by this method, we'll have to actually use chain rule twice. Once to differentiate sine square x for this step, and then obviously we're doing it for the overall function. So we won't always need such complicated things in physics, but it's a good thing to have all this knowledge. Okay. So definitely things like differentiation of sine square x, the one I've done above, or differentiation of that 1 upon square root of some quadratic function. Those kind of things we should know for our physics level of problem solving also. But anything where we'll have to reapply chain rule twice and all that, it's not within the scope of physics. We won't come across something that is that complicated.
So can you please put the slide a little bit up? Sorry, a
Yeah.
little bit down.
Down, okay, sure. Okay, this clear now? So this is going back to the earlier example, actually, this one. So this how we had actually solved, we had actually simplified this. That had made it easier. That we had written this as 2 ln sin x. And then we had put sin x as z. So y was 2 ln z. And from here we had proceeded. So that was easier. But if we had not done this step, then we'd get stuck at this step, dz by dx. And for that, we'd have to do this earlier differentiation, that if a function is sine square x, then what is the derivative of that function? It is 2 sin x cos x. So we'd apply that here. Okay. Now coming to the last part. Oh, sorry, I skipped one
So
thing in
please
between.
wait.
Yeah, wait. In this, I also second part I wanted to calculate. First part was dy by dx. Okay. Second thing is I wanted to find the value of
So
dy
the
by
answer
dx
is
at
2 cot x, right?
yeah. That was which one now? That's this one. That's this one. Okay. But this one I'm talking about sine square x. I wanted to find its derivative at pi by 6 now. So that is 2 times sine pi by 6 cos pi by 6. Or I can directly write that as sine 2x or sine pi by 3 it will become. So you'll see that this is root 3 by 2. Pi by 6 is same as 30. So sine 30 is half and cos 30 is root 3 by 2. So when you solve that, it will come out to be root 3 by 2. Okay, so all this is clear, I hope.
Sir, 2 minutes to.
Okay.
So that simplified which you wrote down, it is that y is equals to 2 ln 7, no?
ln sin x, beta. ln sine square x square. Remember in the previous step how we had done? Ln sine
Yes, sir,
square was
yes.
written as 2 times ln sine x. Okay, so that.
Okay, done, sir. Thank you.
Okay. Okay. Now next what we'll move on to is another application of differentiation. One is, of course, we can find the rate of change directly using differentiation, and we can find the slope of the tangent at any point. That's what we've been doing till now. But apart from that, we can do another thing for a given function, and that is something called find the maxima and minima of a function. By application of differentiation. Okay, so first let's understand what we mean by the term maxima and minima. So suppose, for example, we have a function like this, y is equal to 2x minus x square. So that's my function. Now you notice something here that if I'm, for example, taking positive values of x greater than equal to 0, okay, then what is going to happen is that for a certain amount of time or for certain values of x, the term 2x will dominate over x square. So the function will tend to rise. So for example, if you are going from x equal to 0 to x equal to 1, okay, you can see what is happening to the term 2x. 2x is going from 0 to 2. Whereas what is happening to the term x square? It is going from 0 to 1. So which is dominating? The term 2x dominates. This is dominating, the weight's increasing.
The dominating in the sense.
Because this value is increased to 2 now, whereas x square's value is increased to only 1. So now the function is the difference of the two now. So which one is dominating? The one which is increased by a larger amount. Understood the point?
Yes, sir.
Right. But now in contrast, see what is happening when you're going from, let's say, x equal to, just for contrast, I'll take a much larger set of values. So 5 to 6, let's say, when x is going from 5 to 6, how is 2x changing? 2x is going from 10 to 12. Okay. But what about x square? Is undergoing a huge change. It's going from 25 to 36. What? So this is changing by 11, whereas this one is changing by 2. So which one is dominating? Now this one is dominating. X square is dominating.
Square.
Okay. Now x square and the function is coming with a negative sign. So what it makes it does to y, it starts reducing the value of y. So the value of y will reduce now. As you're going from 5 to 6, now the value of y will reduce because this x square term has increased by a huge amount. Okay. But over here, as you're going from 0 to 1, you can see that the value of y would increase. Because which term is dominating? The term with the plus sign 2x is dominating. So you can understand here that if you just try to visualize the graph of y versus x. So between 0 and 1, I don't know for the rest of it, but between 0 and 1, I realize that y would be increasing. Now I don't know what's happening in between, but at least I can see one thing, that between 5 and 6, you can see that it would tend to decrease. And in fact, if you pay attention, you will see that it has a negative value, okay, and it's decreasing like this between 5 and 6. It's decreasing by a huge amount. So the function is going in this sort of direction. Here it was going in this sort of direction. So in between, we don't know what has happened.
Oh.
Yeah.
So then at x is equals to 2, it would cross that x-axis, right?
Yes, very good. In fact, here you have correctly, you can see that one of the roots of this is x equal to 2. So in fact, another information that we can get is that it's going like this somewhere. And this point must be 2. Okay. But if it's going like this, that means at some point in between it has peaked, before it has come down. So that point becomes a point of interest for us. This, whatever this point is, we don't know, but this is a point of maxima for the function, because it has got a peak at that point. The graph of the function has got a peak. Okay. Now, similarly, like if you think of another example of a graph which has peaks and dips, you can just visualize the graph of y equal to sin x. So you can see the behavior of that function is such that it keeps peaking and dipping and then again peaking and dipping. We discussed about y equal to sin x as a periodic function as x increases.
Yes,
So
sir.
every time you complete 360 degrees or 2 pi, it again repeats the cycle. But you can see that within the cycle, the function is peaking, then dipping, then again peaking, and then the cycle goes on and on. So this function literally now has, you can say, if you take x going up to infinity, it has infinite number of points where the function rises to a peak. Okay. And again, infinite number of points where the function drops to a dip. It keeps going on and on like this. So all of these are maxima. So they're all little peaks. It's all maxima. These are all minimas. So minima is a point where the function dips. Maxima is a point where the function rises to that maxima and then starts decreasing. So you can think of it like a peak in the graph. You can think of this like a valley or a dip in the graph. So there's another minimum. So now see, this graph we know from before. So we have been able to plot it. But given any arbitrary graph, like suppose I ask you x cubed minus 3x, or I ask you the graph of x to the power 4 plus 2x square, or I ask you the graph of 1 by x plus x. Now, it becomes a huge story, that how we are going to plot the graph and how we'll analyze where the function is having a peak or a dip. So given any function like this, now don't worry about all these functions I'm giving you. I don't want you to get confused. But the whole point is that given any function's formula, we can use differentiation as an application very cleverly to find the points where the function is either having a peak or a dip. These points are very easy to find using differentiation. And in a moment, I'll explain to you why they're easy to find. Okay. So before that, from these examples that we've seen in these graphs, okay, let's first define what is a maxima and a minima. So actually, we will make use of a more technical term over here. We will use the term local maxima.
So could you wait, could we write that upper graph part?
No, wait, let's do the conclusion of this, then you write it down, okay? Because this is the proper definition now, what is maxima. So local maxima is that for any given function, y equal to fx, okay, if the graph increases to a peak and then decreases thereafter. Okay. The point at which fx reaches the peak value or the maximum value before decreasing is called the point of local maxima for the given function. And similarly, we have local minima. So the definition of this is that again for any given function y equal to fx, if the graph has a dip at a certain point.
So what is written after maximum value before?
Decreasing. Okay. So if it has a dip at a certain point, okay, so that means such that the function decreases up to a certain minimum value, and thereafter it increases. This point is called the point of local minima. So again, our whole thing is not to get too much into mathematics over here. So we won't, get too worried about technical definitions and all that. Our thing is more about how we can use calculus to find such peak points or some dip points for a given function. Okay, so here is just to get an idea of what we mean actually by the term local maxima and local minima. And then next section, when we see the application of calculus, you will see that. So if this point is A on the x-axis and this point is B on the x-axis, and this curve is the graph of the function fx. So you can see over here that fx increases up to the point x equal to A and then decreases after that. So that means at precisely the point x equal to A, the function has a peak point. So that point is what we call the local maximum. Similarly, you can see that going beyond A now, up to B, the function is decreasing. Decreasing means as x is increasing, the value of y is decreasing. Up to x equal to B. And after that, again it starts increasing. So therefore, at x equal to B in this imaginary graph, okay, the function has a local minimum. Now the actual example of a true function that has this property, one example of that I've shown you above, which is the sin x graph. And you can see that the graph of y equal to sin x has local maxima, that is peak points at so many points, x equal to pi by 2, 5 pi by 2, 9 pi by 2, and this list goes on. And similarly, it has local minimas or dips at x equal to 3 pi by 2, 7 pi by 2, 11 pi by 2, and so on and so on. So really, given this, we'll realize with a bit more practice that a function's graph can have any combination of these maximas, minimas. We can have a function which has no maxima, minima. We can have a function which has infinite number of such peak points and dip points like the sin x one, or we can have a function which has some limited number of peaks and dips. Like this example I showed you, 2x minus x square. I will do the precise calculation for this one also later when we learn the method of using differentiation for calculation of maxima and minima. Okay. But this one will show that it has only one peak point and it does not have any dip point. Okay, but how I know that? Okay, just looking at the function 2x minus x square, there's no way to guess that. So because I have used calculus on this, I've applied that method, so I can say with confidence that yes, I'll be able to show you that this function has one peak point and no dip point. Okay. So where that knowledge is coming from, that is coming from the application of differentiation. So that's what we learn in the next part here. So just note down up to here first.
So sir, the highest point is the local maxima and the lowest point is the local minima.
Yeah, now see, the thing is not like we can't really say it is the maximum wala point or the minimum wala point, because like you can be
Like the point from which it would change, like it would fall
yes,
or rise.
correct. That's the more correct way of saying, because the graph of the function could be like this, no? So it has so many different peak points. So can I say that at this point the value is maximum? No, no, because it's gone more than this here. It's gone more than this here. But this is where the behavior of the graph is changed. It's got a peak over there because it was increasing, and after this point it was decreasing. So over here it's reached. That's why we use the term local maxima, because it's locally maximum. It's not that everywhere it's maximum over here. There might be some other point where it's going beyond that. There may not be. It depends. Okay.
Okay, sir.
Sir, can you scroll down?
Yeah.
This page is completed.
Okay. Okay. So now this was our next example, the sin x graph. Okay. And after having understood a little
The
bit more
local
about
minima.
maxima and minima, okay, we also looked at this. Okay.
Scroll down, sir.
Yeah.
So, sir, so like local maxima will be like a temporary maximum point which we find out.
You can say it's like a temporary maximum point also. Hence the term local. Like it might not be the maximum overall. It may be or may not be. It depends on the particular function that we're talking about. Okay. But definitely it is within that local neighborhood, it's the maximum. So we call it the local maximum. Similarly, local minimum.
So like it is like temporary only for like
The term local is
function.
similar.
Okay, so like there might be or there might be not like a point which is more greater than that.
Exactly. Okay, so later we'll see there's
So
also
can you
another term called global maxima and global minima also. Okay, but right now we will only concentrate on local maxima and minima. So now you see the two definitions that we've written for local maxima and local minima. While you're going through the definition, see how it corresponds to the example below of the graph. Now, it's not some real function. I've just imagined some function. But suppose the graph of the function is like this. Then you can see that at the point A, it is satisfying the definition of local maxima. And at the point x equal to b, it's satisfying the condition or the definition that I've written for local minima.
Sir, my upper portion is.
Sorry, coming in better?
Sir, my upper portion was left right.
Okay, okay. This part, no?
Yes, sir. Yes, sir.
Sir, I was writing the downward portion.
Okay, so this is done now.
Yes, sir. Done.
Yes, sir.
No, sir, no, sir.
Okay.
So can you please read the last line?
And fx is decreasing up to x equal to b, and afterwards again increases. Okay, so that implies that at x equal to b, the function has a local minimum. And that is the same thing as saying that it has a dip. Okay, it's clear now.
Yes, sir.
Okay. Now next thing, see, we'll understand. Just we'll understand this visually.
So 1 second, that last
Sir,
sentence.
you
is not
wrote
written.
something after local maximum.
Yeah.
So can you?
Just a second.
So can you please scroll up? Yes, sir.
Yeah.
Thank you.
Just a minute. Yes. Okay. This part now.
Yes, sir. Done.
Okay, done.
Done, sir.
Yeah. So now, just given some arbitrary function, it's very difficult to guess where the function would have reached a peak, where it would have reached a dip. But if I think about slope of tangent, you'll see that I get a little bit more idea about the function. Okay. So for example, if I'm now just concentrating on a peak point like this, in the graph of a function, y is equal to fx. So at the point A, you can see it's reached a local maximum. Now, what do you think would happen if I drew a tangent at some point like this, the one I'm drawing now, at A minus delta x? If I draw the tangent, how the tangent should look? Should it have a positive slope or a negative slope?
Sir, positive.
Definitely, it has a positive slope. No? So if the function is reaching a peak at the point A, then if I draw a tangent at some point a little before A, it should have positive slope. Okay. Whereas if I draw a tangent at a point a little bit after A, definitely it will have a negative slope.
Negative.
So if I draw at A plus delta x, you can see the tangent at this point, it has a negative slope. Okay. Now what I can say about the point A precisely? At the point A precisely, if I draw a
Sir,
tangent,
0.
yes, very good. It should be a flat line because that's how the function is behaving. No? Okay. So what I notice is that if fx has a local maxima at that point A, then derivative of x, that is f prime x, should be positive at x equal to A minus delta x. And I can take delta x as I like. I can take it as 0.1, I can take it as 0.5, I can take it as 1, whatever. Okay. Should be 0 at x equal to A. And again should become negative at x equal to A plus delta x. That's what the graph is showing us, that it should be having a positive slope a little bit before A negative slope a little bit after A, and precisely at the point where the peak has come, which is the point A, the slope should be 0. Now this is quite easy to work out now, because given a function, we know how to differentiate it, and we can easily check that at which point the derivative is becoming 0, at which point it's positive, at which point it's negative, right?
Yes,
So,
Okay. Now you must have understood that similarly, we can do an analysis for a point where the function is having a minima. In fact, we can see in the same graph. If I were to say, suppose continue this graph, and suppose the function was behaving like this, that it did this. So at the point B, it's reaching a minimum. Now what you are observing here, that at B, if I draw the tangent, again it will be 0. It will have a 0 slope. Okay, but this time the order is opposite. It is negative before and positive afterwards. Here it is having a negative slope, and afterwards it's having a positive slope. So what I can see is that if the function has a local minima at x equal to b, then the derivative should be, so by derivative we can also say slope of tangent. Be negative at x little bit less than b, exactly 0 at x equal to b, and again should change from negative to positive, because the function's behavior is changing from falling to increasing, from dropping to increasing. So this now becomes something achievable for us, this goal. That because given any function, by now we know how to differentiate the function. Okay? And by analyzing the slope of the tangent at various points, that where it's positive, where it's negative, where it's 0, we should be able to tell quite easily that okay, the function is reaching a peak at this point, it's reaching a dip at that point, like that. So this is a sort of like an investigative method, you can say that. Using differentiation, we can investigate about some function whose graph we don't know from before. And investigate that what the probable shape of the graph is, where it's peaking, where it's dipping, all these things. Okay, so after having defined local maxima and minima, now we are seeing how to relate it with differentiation, that what property the derivative has at a point of maximum. At a point x equal to a, if we have a maxima, that means the derivative should be 0 at that particular point, and it should be positive a little bit before that and negative a little bit after that. Similarly, at the point B, if it has a dip or a minima, then it should have this behavior. It is 0 at B, negative before B, and positive after B. Okay, so hope this theory is clear to all of you.
Yes,
Yes,
sir.
sir. Could you take an example of a function? a
Yeah,
graph?
exactly. So now we'll go back to that first one that we were talking about, no? X square minus 2x. I think that was the graph
Okay,
we were talking
sir.
about, 2x minus x square. Okay, so see, we had understood a little bit about it just by taking some arbitrary values. What we had understood so far, that we saw that, okay, at 0, the value of the graph was 0, the value of the function was 0. Then we also understood that initially, which was dominating, 2x was dominating. So the function must have been increasing from 0. But we also realized that somewhere afterwards, it must have been decreasing also, because it crossed the x-axis again at 2. And then by the time we went to 5 and 6 and all, it was like rapidly decreasing because of it. So it must be having some kind of a behavior like this. So we are trying to reconstruct. We understand that somewhere in between here, it must have reached a peak. So we don't know where it's reached the peak. So this is where now it's going to help us. So this is our function. So what we need to do is, so far what we have understood that it must have some kind of a maxima somewhere between 1 and 2. So probably it has a peak somewhere. In fact, let's widen it and say that somewhere between 0 and 2 only. Maybe between 1 and 2, but definitely between 0 and 2, between x equal to 0 to x equal to 2, it's having a maxima somewhere. It is having a peak at some particular point. Okay. So where exactly, let's try to find out. Okay. So for that, we will use that property. So the function for us is 2x minus x squared. So what about the derivative of the function? Just differentiate this.
2 minus 2x.
2 minus 2x, very good. So you can write it as 2 into 1 minus x. Now we can analyze from this very easily that what is happening, this derivative is becoming 0 only at one point. F prime x is equal to 0 at only one point in the entire values of x, which is 1. Okay, so there is only one point where there is either a peak or a dip. That's the first thing that we understand. So it has only one, what we call critical point. That is, it's critical to this thing, that either a critical point is either a peak or dip. Okay, so either the graph of the function should be something like this, it has one peak point, or the graph of the function should be something like this, one dip point. But now from our earlier analysis, we know that probably this is which type of point, it's a peak point. Okay. But let's confirm that analysis. Okay, and then it's actually happening exactly at x equal to 1. So that means that peak point is exactly at x equal to 1. Okay. Now secondly, we can see that for x equal to, let's say, 0.8 or 0.6, let's see what is the value of f prime x. So just put x as something less than 1. What kind of derivative you're getting? You get positive. Checking it.
Yes, sir.
Whereas for x slightly greater than 1, so let's take 1.2 or 1.4 or any of these values. What about f prime x? The moment x is becoming even slightly greater than 1, this thing is positive. So you can see, sorry, this thing is negative. You can see this. Okay. So now what we can tell about the behavior of the function, if this is your x-axis, you have one critical point which is 0. Okay. Now what is happening to the slope before 0? It's positive. So the function must be rising. Sorry, the critical point is 1, not 0. X equal to 1. Okay. So you can see that here the function is rising, and after 1 the function is dropping. So that means this is a point of, this must be a peak point. So it must be a point of local maximum. And there is
Sir?
no other point where the derivative is 0. No? So that means it does not have a local minima. It does not have a dip anywhere, this function. So what we'll further analyze, so what the final conclusion is that for the function fx equal to 2x minus x square, okay, this has only one point of local maximum, okay, and that is at x equal to 1, and it has no point of local minimum. Okay, and now we can even analyze the graph, and we can see that, okay, with little bit more calculation, we can see that if we were to look at the overall structure of the function, okay, now we've already seen that it passes through the origin at x equal to 0 is 0. Already seen that it passes through the point 0 comma 2 because y becomes 0. But now we are also understanding that in between at x equal to 1, it's reaching some kind of a peak point. Okay. And at that peak for x equal to 1, what is the value of y? You can see it is 2 minus 1. So that's also 1. So it's passing through this point. So that means in between it's peaking like this. And we've also analyzed what's happening for x equal to, like, let's say, for example, 10. What will the value of y become? It will become 20 minus 100. So it's minus 80. So it must be going very rapidly down like this. Okay. For x equal to 100, you see even more. It's minus 200 minus 10 to the power 4. So y is like, minus 900 and something. How much is it? Sorry, 9,000. It will be 200 minus this, no? So that will be 9,000.
9,800.
9,800, yeah. So it's minus 9,800. Okay. So you can see that as x tends to infinity, what will happen to y? It will tend to minus infinity. Because that minus x squared term will become huge. Similarly, you will also see on the negative side, at x equal to, for example, minus 1, what is the value of y? It is becoming minus 3. At x equal to minus 2, what is the value of y? It is becoming minus 4 minus 4. So that's minus 8. Okay. And like that, by the time x becomes like something like, let's say minus of 100, y will become like minus of now 10 raised power 4 plus minus of 200. So it will become minus 10,200. Okay, so it's like very rapidly decreasing. The graph is like this. So now we can see that with little bit more analysis, it completely makes sense what we've got from calculus earlier, that this function is not having any minima point. It's only having a maxima point, and that is at x equal to 1. And after 1 again, it starts to decrease. So this whole analysis thing takes a bit of experience, okay, and it like takes a bit of effort in maths also, not just the basic calculus part we're doing in physics. But just to find the peak point or the dip point, we can very easily use this analysis.
Sir,
Yes,
why you took 1 as the critical point and not 2?
because they're going to critical point kaun sa point hai? It is the point at which derivative is becoming 0 now. So derivative is which one? It is this. So 2 into 1 minus x is 0. So that gives me what solution? X equal to 1. There's no other point at which.
Such a derivative of a constant is 0 like this, no?
No, beta, you're confusing two things. I'm not saying the derivative of the function is 0 throughout. I'm saying derivative of the function is 0 at a certain point. Slope of the tangent is 0 at a certain point. See, go back to the earlier diagram. Now you'll see that at any point where the function reaches a peak or a dip, particularly at that point, what is the slope of the tangent? It should be 0. No?
Yes, sir.
You're understanding? It's not that the dy by dx is 0. Dy by dx is f prime x. It's some non-zero quantity, but it's becoming 0 at a particular point, and that point is called the critical point. So see, for this function, what is dy by dx? It is 2 into 1 minus x. So this 2 into 1 minus x is 0 only at a particular value of x. No? Any other value of x is not 0. And that particular value is which one? X equal to 1. It's clear now?
Okay, sir, thank you. Yes, sir.
Yeah.
Sir,
Yeah, yeah, beta.
to find the value of x, we will use fit and trial method.
Matlab, we'll have to find the roots, na? Like f prime x ko 0 I substituted. Now f prime x here was what? 2 into 1 minus x. So that's become a maths equation for me, na? That 2 into 1 minus x is equal to 0. So I have to solve for x.
Oh, okay, okay.
So in
And,
maths, we say that is the roots of that equation. F prime x is equal to 0. So what is the value of x? So that is the root of that equation. So in this case, there's only one value of x. So that equation has one root, and that is x equal to 1.
Okay, sir. So means number of critical points will be the power of the polynomial.
Very good question, beta. So think like this, na? See, number of critical points will be the number of roots of that equation, na? That f prime x is 0. Now, if f has a power of n, then what is the power of f prime x? Maximum power is 1
N
less
minus 1.
n minus 1. So that will become the number of roots actually.
Okay, sir. Thank you. Got it.
So here the function was quadratic. So the derivative is linear. So there is only one critical point. If the function had been cubic, then the derivative would have been quadratic. Now quadratic equation can have up to two roots. Na?
Yes, sir.
Okay, but it can also have less than two roots. Remember, quadratic function need not have two roots. It can have a common root or it may not have roots also. So all the possibilities are there.
Okay, sir.
So, sir, the more the number of roots, the more the peaks or the dips.
Yes, the more the peaks or dips. Okay, so when you think of a polynomial function, if it's of the type, if it's like a cubic function, then it can have up to two critical points. So it can have a peak and a dip. If it's a power 4 function, let's say, it can have had three critical points. So it might have two maximas and one minima, or one maxima and two minimas. Any combination like that it can have. Like that, if it's, let's say, a polynomial of power 10, x to the power 10, then it can have as many as 9 critical points. Okay, and 9 critical points means, 5 of them can be maximas and 4 of them can be minimas, or vice versa. 4 of them can be maximas and 5 of them can be minimas. So this thing gets a little bit complicated. I don't want to get too much into technical maths over here. We will just keep it simple, what we need in physics. And with some more examples next time, we'll see like how to use differentiation to just quickly analyze simple functions like quadratic function or cubic function and find the peak and dip points.
So after this also more is there, or this is the end?
Yeah. After that, then there is integration, which
Sir,
is very
no,
easy.
this which you wrote after this slide, like I have wrote this page.
Yeah, now there is this partner. We analyze this graph. Okay. So this thing you understood now, how we investigated for the critical point, right?
So kind of scroll up.
Yeah.
So for the major test, we will also have integration.
Only the basic formula of integration, beta.
Okay, sir.
What is the date of your major test which sir is given now?
So this Sunday.
So 25th.
25th. No. Then in this major test you will not have integration. It's only going to be up to here.
Okay, sir.
Okay, sir. सर एक सेकेंड के लिए कैन यू ऊपर कर सकते हो एक सेकेंड सर लिटिल बिट मोर to see some previous thing.
Yeah.
Okay, sir, done. You can go to the original page.
Okay.
Done, sir.
Okay, people. So that's it for today's class. Yeah. For the
For
upcoming-
finding out the local number of local minima, like we don't have any proper formula, like we have to check it.
Yeah, you have to, like, next time now we'll discuss that there's a systematic process that involves differentiate the function, put the derivative equal to 0 and find the number of roots. Then we do something called second derivative test, which gives us an easier way of analyzing whether a given point is a local maxima or a local minima. So for example, suppose we differentiate a function and put it equal to 0, f prime x equal to 0, and we get 3 critical points. Then there is another method by which we can tell which of those critical points are maxima and which of them are minima. Okay, but that will require to learn few more things before that. So we'll do that in the next lecture. So for this upcoming major test, just concentrate on the application of differentiation up to chain rule. That is, you should be able to differentiate any type of trigonometric, exponential, or log function given to you, including the like the composite functions, like the type we've done today, that it is ln of sine x, or it is e raised power some other function like e raised power x square, or e raised power some trigonometric function, e raised power tan x or something like that. You should be able to apply the chain rule for those type of functions. Understood, no?
Okay, sir.
Yes, sir.
Okay, so that's it for today's session, people. Wish you all the best. Thanks for attending.
Thank you, sir. Have a good day.
Thank you,
Bye,
sir.
sir.
Bye.
Excuse me, sir.
Yeah, beta.
Sir, this is not related to the syllabus. I just wanted to ask, sir, is Purple House the last batch?
No, I think there has been one batch after that. No? There is Indigo House also, and then there's another batch called Foundation.
Okay, sir. Okay.
Any
Thank
particular
you.
reason you're asking, beta?
No, sir. No particular reason.
Acha, matlab you have some friend who wants to join or something?
No, sir. I joined after my friend.
Okay, okay.
Okay. Thank you,
So,
sir.
you're worried about the pace of the syllabus and all, no? We will do some catching up like later. So you
Yes,
have
sir.
like 2 years to go, no? So you'll be well on time for the completion of syllabus and all. Don't worry. Okay,
Okay, sir.
okay, okay. Beta. All the best.
Thank you, sir.
Thank you, sir. Have a good evening.
Thank you, sir.
Okay, beta. Bye. All the best.